Thank you very much. And thank you all for coming, and I'm glad to see some old friends and familiar faces. So happy to be here. And my topic today is about privacy-preserving data collaboration. And for the ones of you who are familiar with what we call PETs, privacy-enhancing technologies, we'll be talking a little bit about confidential computing, homomorphic encryption, secure multiparty computation, and all these techniques. And then, so I'll introduce them from the concept of data cooperatives, which is all about data sharing and collaboration in a privacy-preserving way. We'll go through some of these techniques, in particular, confidential computing, secure multiparty computation, and homomorphic encryption. I'll give you some examples of projects that we've run and that we are running as we speak. And then we'll conclude with some considerations on how these techniques can be used in the context of GenAI, LLMs, in particular if you wanted to use third-party owned models that are available out there on the internet, like ChatGPT. So a few words on me. I'm Giuseppe. I'm one of the senior managers at the Accenture Labs in France. The Accenture Labs is basically the R&D organization within Accenture. We are basically the guys who are behind the tech vision, so the guys who are looking at things that we will sell to our clients in the years to come, and we are starting to incubate and qualify the technology before Accenture takes it over and to bring it at scale. And I've done a lot of incubation work around blockchain technologies, identities. Now I'm looking at privacy-preserving computation, as well as robotics, and as you will see from my presentation, we are also getting into high-performance computing, especially for GenAI-related type of requirements. So data cooperatives, what do we mean? It's all about data collaboration between different organizations who want to share their data, collaborate on data without sharing the data. So we talk about protection of the data while in use, not only at rest and in transit, so that we can extract additional value from the data, especially when we aggregate it from sources that do not necessarily trust each other. And this is cross organizations, but it also can be within the same organization between departments that do not trust each other or for some legal reasons cannot share the data between themselves. And of course, this plugs into all the concepts around data mesh, data products, especially when you have to pull data from different sources and you want to protect the data themselves because they contain PII, personal identifiable information, but also IP, especially when you want to protect models that you want the others to use. So a bit of context, especially with and after the COVID, we've all discovered the value of data sharing and collaboration. If we think about all the vaccine and all the collaboration that was around the COVID and the vaccines that were explored worldwide, definitely there is a need to unlock additional value from the data, but at the same time, regulation and data sovereignty requirements impose companies to be very, very careful if you think about GDPR on the way they handle PII. If we look at Gartner, these days they say that by 2025, 60% of the large organizations will use some of these techniques, especially in untrusted environments, for example, while moving to the cloud, but also to power what we call multi-party scenarios. So those multiple organizations who want to collaborate without giving the data away. So in terms of context, especially legally, data residency is a very, very important topic. Data cannot really move cross-border. Europe GDPR is an example. And also, data cannot be used for secondary purposes, which is different from the primary purpose for which the data have been collected. And this is very true for PII, personal identifiable information, but also for other type of data that are not necessarily PII, but include trade secrets, IP belonging to the company that, of course, you want to protect when you are collaborating. That's why we came up with this concept of data cooperative, really as a construct to enable collaboration between different organizations while preserving IP, privacy, as well as compliance. And PETs, privacy-enhancing technologies, then become a tool so that we can really protect the privacy and the confidentiality of the information while in use. So traditionally, we protect this data at rest, in transit. Now we want to protect the data while we process them, while we run queries, while we train a model, especially if we aggregated information from different sources. So that's a little bit how we introduce the topic with this Lego analogy. So without data sharing and collaboration, if you think about three organizations, A, B, and C, they all have their data sets, they all have their people and their tools, and all they can build is something more or less sophisticated, depending on the quality, depending on what they have, especially when it comes to the data, and also these days, the power that they have in terms of computing. So what we are saying is that with a data cooperative, which is, we can create something that is privacy preserving in a way that A, B, and C can aggregate the data and build something together which is way more sophisticated than what they could build individually. And we want to do this protecting the data while in use, so that B cannot see the data coming from A and C and all the other combinations. So that we can train a model together, for example, for illness detection, for anti-money laundering, so that we all benefit from a much more powerful model without being able to see the data coming from the different contributors. And of course, this is true for data sets that we want to aggregate, but we can also tweak it in a way that instead of just protecting the data, we also protect the models. I have a model, I want you to use my model, but I don't want to give the model away, so that you can encrypt your data, send them to my model. Potentially, my model is able to handle encrypted data, and you infer from my model, so that I cannot see your data and you cannot see my model. And there are different ways to do this. We'll see in a second. So what's possible and which are the trends that we see today? Of course, multi-party collaboration, like the Lego slide, is a bit the dream. But from a governance standpoint, that's quite complex. The business model is not straightforward. And also regulation compliance is tricky, but the regulators are starting to understand all this. But in general, we are now seeing, especially when it comes to these technologies, three different trends. No collaboration with others, but I'm simply migrating to the cloud, and I want to protect my data and workloads from the hyperscalers, from the cloud infrastructure providers. I want to move my data on Azure, GCP, or AWS, but I don't want Microsoft, Google, and Amazon to have access to my data at any point in time. So I move the data encrypted, or I use some confidential computing to keep the data encrypted using some hardware technologies. Another trend is more a one-on-one type of collaboration, where I have the model, you have the data, and the other way around. We want to use each other's resources without giving them away, not only for data confidentiality, but also for IP reasons, especially if I want to protect my model. And then the last one is the multiple organization, which is the Lego slide. So all together, we want to train a model together. So in a way that I cannot see the data coming from each of you, and all of you applies the same. So these are the three patterns. If we look at hyperscale cloud providers today, they all started to offer trusted execution environments, confidential computing. So for the ones of you who are familiar, here we talk about Intel SGX, TDX, AMD SCV type of CPUs, AWS Nitro. Those are all technologies that use hardware protected environments, so that a portion of the memory of the CPU is encrypted, hardware encrypted, so that once you load the data in that portion of the memory, you can process the data, but outside of that portion of the memory, nothing is basically visible. This is a reality, this exists, we are using it today with clients. Other technologies, as you will see, especially homomorphic encryption, secure multiparty computation, are evolving extremely fast, but especially in the context of AI, from a performance standpoint, we have to be careful on what we engage with, because given the complexity of the models and the size of the data sets, encryption and protection while in use can become tricky, especially if we want performance and speed, especially when we move towards the edge and we simply do not centralize everything in the cloud. So these are a bit the trends. Reality is trusted execution environments are available. SMPC is getting more and more available. Homomorphic encryption is evolving very fast. Some use cases can be supported, but there is work to be done with homomorphic encryption. So let's demystify a little bit all this. So what are privacy-enhancing technologies? So I like this diagram, but of course, this diagram can be interpreted in many different ways. But in general, we have 3 families of pets, and all of them address different objectives, and the reality is that what we see today is really the combination of multiple techniques, because there is no silver bullet for a single use case for the different techniques. But definitely, there is a way to shield data. So you simply tokenize, use homomorphic encryption to encrypt the information, or zero-knowledge proof, really to hide or shield some private information that you have in your dataset. Then there is the possibility to alter the data by injecting noise into your datasets. That's differential privacy. And of course, you can fine-tune the level of noise depending on the compromise between usability of the dataset and security. And then you still have the option, which is definitely a good one these days, of generating synthetic data, assuming you can generate good synthetic data. And then there is the possibility to federate data coming from multiple sources. And you can do this with the trusted execution environment if you create something that we call clean room, where different providers can bring the data in. In the clean room, you hardware protect the data and you manipulate the data. Secure multiparty computation. Data stays at the edge. The different contributors only exchange secure shares. They do the calculations so that no one can see the inputs coming from the others. Federated learning. You push the model at the edge. You train at the edge. No data moves. You just get the models that have been trained at the edge, and you create a global model, which is basically the combination of the different inputs coming from the edge. And that type of aggregation is something that you can do combining federated learning and secure and trusted execution environments. So you get the different models and you combine in an hardware protected environment. And then you can do private set intersection, assuming that your data sets have some common attributes, so that you can combine and build those aggregated data sets on some common attributes in a way that is privacy preserved. So this is a little bit the spectrum, and as I said, no silver bullet. This is all maturing extremely fast, some faster than others. And the reality is that, especially for GenAI, we are seeing the combination of multiple of those to become more effective and scalable. So as I said, traditionally, we've been focusing on protecting the data at rest and in transit. Here we want to talk about protection in use. The technologies we are very active on as we speak, at least in the labs, but I think also in the community out there, are trusted execution environments, and we'll see this much more into the details in the next minutes. Differential privacy, it's something that has been out there for years, so nothing really new there. Now, there are more sophisticated ways to inject the noise so that you can really fine-tune the usability versus this level of security that you want to achieve. Homomorphic encryption, we'll get into this in a second, as well as secure multiparty computation. And then federated learning in itself does not use any specific cryptographic technique unless you want to increase the level of security, especially when you aggregate the model. Because it's been demonstrated that if we do federated learning and you all send me your models for me to aggregate, if I am a malicious server, I can reverse engineer your models and go back to your original datasets. So that's why you want to start combining federated learning, for example, with trusted execution environments, so that when I aggregate the global model, I cannot see your inputs. This kind of thing. So last slide on the opportunities and so on. What are the opportunities today? It's all about identifying sensitive information, easy when it's PII, but it's not just about PII, there is also a lot of IP. Think about the interactions that employees from different companies have with ChatGPT. This is not just about the query, this is also about 3-4 queries in a row that can reveal a lot about your IP. And then, depending on the different requirements, depending on what you are trying to do, the scale and the complexity, different paths are available, and people really need to assess the effectiveness of those techniques depending on the requirements and on their objectives. But really, if we wanted to summarize all I said today, at least so far, we are talking about technologies that can support two types of use cases. Data must remain confidential during processing and analytics. And the other spectrum is you do not protect just the data, but also the algorithms that will process those data. And you can do both at the same time. So let's look at the three that I mentioned a little bit more into the details. Trusted execution environments. Those are what we normally call secure enclaves. There are different ways of implementing secure enclaves from an hardware standpoint. Intel was probably the first one with SGX. Now they also have TDX, AMD, NVIDIA is coming up with a solution on their GPUs, as well as ARM for their type of processors. This example that you see on the slide is a standard clean room. We call this a clean room, right? So this is the solution where you have multiple participants who have data, they encrypt the data, and then they move the data into this clean room. In the clean room, the data are stored kind of encrypted, and then once they are loaded in the secure enclave, they basically can be processed because after the attestation, the decryption keys are made available by the different participants. So really look at this as a portion of the CPU, and that's the only place where the data can be decrypted and processed. And processing the data means running some Spark queries or training a machine learning model. This is a clean room. This is probably the easiest way to use confidential computing, but there are also other options where instead of having multiple participants, you only have one participant that is migrating to the cloud and wants to protect against the cloud provider. Something very important is this concept of attestation. That is something that every participant will do before moving the data into the clean room. And the attestation enables building trust against the clean room. So that when I call the attestation service, I'm expecting the attestation service to come back to me and say, this is a secure environment, this has been patched, there is integrity in there, it's safe to move your data for processing into the secure enclave. And we've done a lot of work on this, and I have a few examples in my next slides. From a trust standpoint, if you think about the attack surface of especially this type of processing, and while moving to the cloud, if you do not use confidential computing, really from the infrastructure employees up to your application, going through the CPU, the BIOS, and the hypervisor, everything is accessible. So if someone has access to that environment, people have access to your data and your workload. If you start using things like Intel SGX, then your surface of attack is reduced a lot, quite drastically. Basically, what we are saying is that in a portion of the CPU, you will run a secure portion of your application in a way that nothing is accessible to anyone else that has access to that machine because the data is hardware protected. This is the Intel SGX, and this is the most sophisticated and probably the solution that gives you the highest level of security. Then you have confidential VMs, where it's not just about protecting a portion of your data and a portion of your application, but the full VM is encrypted, which basically means that you may want to use this for lift and shifting your existing applications into a VM that is confidential, versus here, you may want to consider Dockerizing your existing applications and port them into the SGX, or, depending on the level of sophistication, rebuild your application so that they can run safely into an SGX. And then also Amazon came up with what they call nitro enclaves, that do not really offer a built-in encryption, but give you the ability to do some segregation of privileges within your application. This is a solution that relies on two VMs. One is secure, one is less secure. And then you really have to split your application in two and deploy the part that you want to secure into the secure enclave. But of course, this is giving much more, this is allowing for a much wider surface of attack, and it's not really designed to protect against the infrastructure providers. And then all I wanted to say is that on top of all this, if we think about GenAI and NVIDIA GPUs, for example, NVIDIA GPUs like the H100s now are starting to support confidential computing with a project that is called Hopper. So basically now you can run an H100 together with AMD SCV or with Intel TDX. And basically there is a solution where there is a buffer so that you can move the encrypted data between CPU and GPU in a way that once the data is safely stored in the GPU, confidential computing applies, you train your model with the GPU, and then eventually you go back to the CPU using the encrypted hardware as well as the encryption over the buffer that sits in between CPU and GPU. Homomorphic encryption. This is fantastic, but from a performance standpoint, here there is work to do. Homomorphic encryption normally comes with a set of libraries that let me encrypt the data, keep the encryption key, send the data to you so that you can run your algorithm, you can do your calculations without having to decrypt the data, come up with an output which is encrypted and that you cannot decrypt. You send it back to me, and I am the only one as the data owner who can decrypt the information. So all software, no hardware to trust. I am the owner of the encryption key, and I keep it with me. That's the fantastic approach, but from a performance perspective, it's very heavy because there are many different ways of implementing it, but there is a lot of noise. There is the concept of bootstrapping, and the more operations that you run, the payload becomes bigger, and at some point you need to stop and reset. There are different ways of doing homomorphic encryption. The one we are looking at now is full homomorphic encryption that allows you to do both additions and multiplications, but of course you have to rewrite your algorithms using those applications. And of course this has some limitations on what you can do today. But in the slide you see an example, which is what I just described. I am the data owner. I have the key, I have the data, I encrypt the data, I send you the encrypted data, you are the computation executor, you do your calculations, you have a result, but that is encrypted, and in order to see the result, you have to send it back to me, the data owner, and I am the only one who can decrypt. You will see in my next slides that this works for things like secure query, to train statistical type of models, still too heavy for GenAI and neural networks in general. It requires hardware accelerations on dedicated ASICs. This is in the making. We believe that in the next 5 years, this will become much more viable thanks to hardware acceleration. Today, it applies to a number of use cases that need to be carefully discussed. And then secure multiparty computation, which doesn't have to be confused with the federated learning, because this is not just about training a model. Here you could do any type of calculations between different participants. The idea is that each of them keeps the data where they are, and then using MPC protocols, they only exchange secure shares, both for the data and for the algorithms. We do this calculation together. Each of us does a portion of the calculation on a portion of the data by only sharing those secure shares. And then there is a reconstruction process where we put together all the individual results and we come up with the final and global results that we all want to achieve together. Of course, this works. This is a reality. We also, as Accenture, invested in a company that does SMPC. The company is called Triple Blind. Very strong in healthcare and in financial services, but here, of course, there is some overhead from the orchestration of the consortium as well as from the data exchange that becomes bigger in terms of payloads, depending on the complexity of the model and the size of the data sets and so on. So with that, we described data cooperatives, the challenges that we have, and few of those techniques. Few sample projects. this is something that we've done for the central bank in France last year. This basically was the central bank and the regulator who wanted to prove that these technologies can be used to pull data from the different banks to train anti-money laundering model without each bank being able to see the data, the transactional data coming from other banks, also because they are not allowed to share. We could have done a clean room with confidential computing where all the banks pull the data into the clean room, but we decided to do it with the SMPC so that the data stays at the banks. They only share secret shares and the datasets as they are do not have to be encrypted fully and of course do not have to move. So we used this solution from this company, Triple Blind. Imagine the three banks using one of those triple blind access points that allow to build this peer-to-peer network. And basically, each of the banks is positioning the data into this access point. And then, depending on the type of algorithm, the access points talk to each other to basically implement secure multiparty computation to query the data from each other, train a model, build a knowledge graph so that we can see that the transactional data go from one bank to another, and then eventually the initial money sent from France to France ended up in a blacklisted country. You can do this using these techniques so that you have a much more powerful model at inference time, but during training, none of the participants can see the data contributed from the others. So full decentralization. We are not going into the details here, but Triple Blind does not really encrypt the data, but they have a one-way encryption, which is not really hashing, but it's definitely something irreversible. And then, of course, once you contribute the data, there is also the ability to define policies so that, yes, you can use my data, but you can only do A, B, and C and nothing else. And then, of course, this is not just about the data, it's also about one of them or all of them together coming up with a model that can benefit from this virtual pooling coming from the aggregation of the data from the three different banks that decide to work together. And definitely we've got very good results here. We've shown that definitely there is a large improvement, especially if you build graphs in terms of fraud detection and fraud reduction, if you pull data from multiple banks, because today each bank can only see the money that comes in and goes out, but they have no idea on what happens to that initial money that originated from here and then starts flying. Imagine building an anonymous graph that allows you to flag transactions depending on the patterns that you start seeing on your own data. Then, using clean rooms, we've done a pilot with a large retailer, actually an holding company that owns a number of retailers. Although this is the holding company and they own the retailers and the data of each retailer, for legal reasons, the different retailers cannot exchange the data between themselves. And then we had to come up with a solution that allows the holding company to analyze the data from the different retailers that they own, so that each retailer could encrypt the information, bring them into a data clean room that we were running on Azure using Intel SGX. On that clean room, you start doing some smart analytics and querying the data to basically start analyzing your spending patterns, identifying your segments of customers across retailers without revealing each other's data. And again, this is in the cloud. This is with Azure in particular, using Intel SGX and one of these tools that allows us to build the consortium, encrypt the data, and do the processing in the cloud in a confidential way. And this is one of the approaches where in the SGX we've taken an existing application, Dockerized, and then used some open source tools like Grameen to basically take a container and bring that container into the SGX without having to rewrite the full application that does the analytics. And then the last one I'm busy today with is this project. It's yet another clean room. We are using a different technology, but probably a bit more scalable. In the clean room, we do a lot of Spark SQL type of processing, but we are getting ready for machine learning. This is one of those projects where you have an administrator and different data contributors. every data contributor has their own data. They encrypt the data, they keep the keys, they move the data to Azure, where there is some cloud storage, where the data is parked, temporarily encrypted. And then the administrator can start basically suggesting some jobs that different data contributors can approve, and then run in the secure query. And once the data are loaded into the clean room, you start decrypting the data and basically do your processing. You get your results, you encrypt the results back, you put them into the cloud storage so that then you can selectively decide who can see the data and for which reason. And of course, very importantly, this attestation service is key, and this is paramount to everything I said. If the attestation service doesn't give the guarantees to the data contributors that the hardware environment is safe and secure and patched in the best way, there is no way they will move the data, even if they are encrypted, because that's something that you cannot get wrong. So this was to give you some examples. So now we use some of these techniques. This was secure multiparty computation, confidential computing. And now I wanted to conclude for the last few minutes on what happens to GenAI. Of course, when it comes to privacy, the easiest answer would be you deploy the model at home, it's private, eventually you fine-tune it, and so on. So that's the easiest answer. But what if we wanted to use third-party models that are out there? And we all know that every time that we submit our context or our prompts, these guys, maybe they are not allowed, but basically they keep using the data to train and retrain their models from our questions. So how we can use some of these techniques to start protecting the data. So as I said, solution providers, they keep training their models with our inputs. The challenge is that from a GDPR standpoint, that's not really compliant. But we also know that the real power comes from the ability to fine-tune the model, to provide some context to the model. So here we are not just about trying to protect our queries, but also the way we start fine-tuning. And ideally, the solution would be to start having encrypted conversations with these LLMs, not only for the prompt, but also for the context. And if we also wanted to fine-tune, also have the ability to encrypt our data set, give our data set to the model so that you can fine-tune the model without having to decrypt your information. Ideally, as I said at the beginning, we would use homomorphic encryption. That's exactly what I said. I have the key, I encrypt my context and query, I send it to the LLM. The LLM has been built in a way that can deal with encrypted information. You infer or you retrain on the encrypted information. You cannot see the inputs, you cannot see the context, you cannot see the results. You send it back to me, I decrypt. The problem is that given the complexity of those models with billions of parameters and the size of the context and the data sets, homomorphic encryption definitely cannot scale. We cannot run this with homomorphic encryption in a cost-effective way. And we've done some estimates without going into the details. Today, this would require a 500,000x type of improvement. Which, by the way, may sound impossible, but from some estimations, and at least how the things are going, we are seeing that this may be a reality in the next 3 to 5 years. Also because LLMs are also getting faster, because we are starting to use those compression techniques that allows us also on CPUs to be much faster and effective with LLMs. Full homomorphic encryption is also getting faster, and that's a fact. And there are a lot of investments, especially there is a DARPA sponsored project in the US, which is all about hardware accelerating homomorphic encryption. And we've seen and we expect, a 10,000x type of improvement on those ASICs for their second generation. So all I'm trying to say is that homomorphic encryption is exactly where we want to be, but for GenAI LLMs, there is work to be done, and this will come probably in the next 5 years due to hardware acceleration. But what can we do until we get there? And I know I have a few minutes left. There is a company called Opaque we work with for confidential computing that came up with the first and probably simple solution to sanitize the queries that we submit to LLMs as well as the context. So ideally, this solution would sit between you as a user and the third-party model. And they run this in a trusted execution environment so that they cannot see what you are asking for and the data that you are using to fine-tune. Basically, they take your data in a confidential computing clean room, they analyze your context and prompt, they tokenize your sensitive information, they submit to the LLM. The LLM is able to reply without any modification. You don't have to modify the LLM. The LLM comes back with an answer that goes back into the trusted execution environment where you desanitize, you replace back the sensitive information that you removed, and you got your user response. First, probably too simplistic solution, but it works. This is up and running today, and it allows you to start protecting your private information when you use these LLMs. Of course, this is for very specific and simple sensitive information. It doesn't help with the IP. A more sophisticated approach we've seen from a company called Triple Blind, where they've built this privacy monitor. And basically here, instead of just sanitizing the information, they also help you with fine-tuning. Basically, you can start ingesting your information from documents, wikis, or data into this privacy monitor. They use a lot of differential privacy basically to build your vector DB, as well as to semantically analyze your dataset so that this helps you with fine-tuning. And then from here, you interact with the third-party LLM to do what the previous company does, but in a much more efficient way, because here you are not simply replacing the words, but you are actually coming up with a much smarter approach so that you can, it helps you with fine-tuning as well. And the last one, just to show you the complexity, if we wanted to do something like this with homomorphic encryption, we would have to kind of rebuild the model, which is not that straightforward, especially if you think about GPT-2, the transformer architecture, encoder, decoders, and the different layers. And Zama, which is a company very strong for homomorphic encryption, came up with a solution where you can split the layers and you run some of those at the client on clear data or inference, for example. Then between each layer, you basically encrypt the information, you send them to the attention module, where the attention module runs on encrypted information, you get back the result, you decrypt, and you continue with the next layers. But this would require a lot of work on the modifications of the model itself, but also on quantizing the information, because you have to bring your data into an integer space and rewrite all the functions so that you can deal with just integers. There is an experiment, there is an open source project out there from Zama. They didn't focus on performance, so it's not extremely performant, but from an accuracy standpoint, they've demonstrated that they can almost have the same accuracy that they have on running the same thing without having to encrypt the information. So again, very promising. It's probably what we want. But from a performance standpoint, we will need some hardware acceleration, which, as I said, will probably come in the years to come, hopefully 5. And with that, I'm done.
Thank you very much for your presentation. We kind of are out of the time, but there are some questions. Maybe you can pick up one or two.
Yes.
Answer.
So the first one, how can we do calculations on encoded data? How does it work in general? As I said, it depends on the technique that you use. If you use confidential computing, once you are in the hardware protected environment, the data is unclear, because in that specific portion of the memory, the data is being decrypted, so you don't have big limitations there. If you do homomorphic encryption, you really have to use libraries that can deal with encrypted information without decrypting at any time. No hardware, this is all software-based. And basically, this is all about moving the data to a different space, injecting some noise that at some point you will have to reset, but you really do it on encrypted information. So you send me encrypted 2, you send me encrypted 3, I know to sum them, I do encrypted 2 plus encrypted 3, I come up with a result, but I have no idea on what it is. I send you back, you can decrypt, and you will find out that it's fine. But I know how to do the sum on encrypted information. With SMPC, it's a multi-party type of scenario where using algorithms like Shamir secret sharing, these kind of things, you start sharing the data and you only start exchanging secret shares between the different participants so that, as I said, each of them runs a portion of the calculation on a portion of the data set and then you have to recompute. But again, you are not decrypting the information, everything is software-based. How do you perceive the regulator pressures to build backdoors into pets? This is a complex question. I don't know if there are pressures to build backdoors, probably in some countries more than others. But that's a regulatory type of discussion that we can probably take offline. How can I debug an application running on SGX? You cannot log the type of operations that you do into the SGX. Definitely not. Basically, this is all about debugging it outside. And then once you know the code runs and in the proper way, you deploy. Again, rewriting your application or lift and shifting. But of course, you cannot debug because you have no access to the data while they are in the secure enclave. And in fact, when we do this type of work, we also demonstrate to the client that if we dump the memory in and out of the secure enclave, there is no way you can access the information. So definitely you cannot debug as is. Is the attestation service a trusted third party? Can it be decentralized? That's where it's going. So today, each of the providers like Intel, but also AWS with Nitro, they have their capability to provide attestations. Microsoft is also coming up with an attestation service on Azure, but here you are trusting Microsoft and then eventually the hardware manufacturer. Now Intel came up with a project that before was called Amber. Now it's called Intel Trust Service, which is basically decoupling the capability of doing attestation from the hardware provider. So this is a software library that can be run by Intel, but also by others that is attesting on behalf of the hardware provider the secure hardware. And of course, that can be decentralized as well. So this is exactly the direction where the attestation is going, and I think it's also the one way it has to go, because I don't want to necessarily trust Intel to attest their own CPU or AMD or Amazon.
Thank you very much. This was the last question, so it's time for lunch. Thank you very much for your presentation. Oh, now we have...
Thank you.